recitation, and I don't have the notes up yet, but it'll be up by tonight. So for now, if you can just listen or take notes, but if you don't want to take notes, there'll be a summary up online. So there are two slightly distinct agendas that I want to cover today. One part of it is going to be about giving you some geometric intuition about strong convexity, Lipschitzness of functions, Lipschitzness of gradients, and so on. And the other one is going to be a smaller part talking about, again, geometric intuitions for operations that preserve convexity of sets and functions, and how you can think about both simultaneously in some sense. About the convexity of sets and the convexity of functions are strongly related to each other through the epigraph of a function. Okay, so let me start off. So the recitation is broadly going to be me telling you a random bunch of interesting things, and so at any point, if you want to stop me, then just stop and go on. Otherwise, I'm just going to start right now. Okay, so let's start off with some properties of convex functions, operations on convex functions that preserve convexity. So one of the most important ones is going to be taking the maximum. And this is, initially it might seem quite obvious, but it can end up being quite subtle, as we'll see. So the claim is that the maximum of two convex functions or a set of convex functions is convex. Okay, so if I have f of x, which is the pointwise maximum of f1 of x to fn of x, anything like that, then this is also a convex. Then f is also a convex function if each of these is convex. Now the most, for a lot of these properties, the way I think about them is through the epigraph. So if you want to show that f is convex, then what you want to do is really imagine the epigraph of these two functions. So you have two convex functions, and if you want to talk about the maximum of the two convex functions, then in this region it's the right function, and in this region it's the left function. And so it's basically that's what the max of the two functions looks like. And the epigraph of f of x is actually going to be the intersection of the epigraph of f1 of x and f2 of x. That's going to be really easy to argue, because any point that's in the epigraph over here must lie above f of x. So if you remember, the definition of epigraph of a function is the set of all points that lies above the function. So all points that lie in the epigraph of f of x, they have to be above f1 of x and above f2 of x. So if they're above f1 of x and above f2 of x, then they basically lie in the intersection of the two sets that are all the points above f1 of x and all the points above f2 of x, which is exactly the epigraphs of those two functions. So it's very easy to see that the epigraph of f of x is the intersection of the epigraphs. And because the intersection of sets preserves convexity of sets, because of that, f of x is also convex, because a function is convex if and only if its epigraph is convex. So, and we know that the intersection of epigraphs is convex, so f is convex. So that's good. So the most trivial example of seeing something like that is you'll often come across minimization problems where the function that you're trying to minimize is piecewise linear. So it's given by something like this, right? So it's you have a bunch of lines, and the function is known to be piecewise linear, either because you constructed it that way or because it's some kind of a piecewise linear loss function that you're trying to minimize, because it could be like a hinge loss, which is the max of 0 and something else. So you'll often be trying to minimize something like a piecewise linear function, and you know that this is convex, so you know you're in a convex optimization problem. So this is like the simplest example that we'll be dealing with. Now things get interesting when you actually note that when I'm taking the maximum of a set of functions, this set of functions does not need to be a finite set that I can count over. This can actually be an infinite set of functions. So this could be like, this n need not be finite, it just could be an infinite set. One example of that would be if I look at the function for any set C, I'm looking at a function like, okay, so this is some function f of x. So it's a function of x, and it's given by max over all y in any set C. The set C may be convex or non-convex of the distance between x and y. So this is basically the value of this point x is its distance to the furthest point in your set C. Now, since each of these functions is convex, so this is just like the 2 norm. Basically, if you want 2 norm squared, that's fine. So whatever, each of these functions is convex. I'm taking a pointwise maximum of convex functions, and so this is convex as well. Okay, so this is a very interesting example, which is not immediately obvious as to why this function would be convex, but basically it's just a generalization of this property that max of convex functions is convex. Okay, there are many more interesting such examples. Another one of them is the maximum eigenvalue, okay, of so f of x is going to be lambda max of x. So here this is a function of a matrix. So yeah, x is a matrix, and the value it takes at any x is the maximum eigenvalue of x. So this is only over the set of all symmetric square matrices. Okay, so I define such a function over that set, and this is the definition of the function. It's not immediately obvious that this is a convex function, but if you think about what the definition of this lambda max is, then it can actually be written as max of u transpose xu, where the norm of u is 1. Okay, so I mean, this is just the definition of what the maximum eigenvalue is. It's actually the vector which, if you calculate this, it's called the quadratic residue. There are many names for this, but you calculate u transpose xu for different vectors, and the vector that really maximizes this is going to be the largest eigenvalue. And this, what the variable here, so this is max over all u, right? The variable, this f of x, this f of x over here, the variable is actually x, right? This is the variable that you care about, and each of these is linear in x, so it's linear in the variable that you're bothered about. The same way over here, each of these terms for any given u, for any given u, this is actually linear in x. It's quadratic in u, but it's linear in x. So this is actually the pointwise maximum of a bunch of lines, of a lot of lines, or hyperplanes if you want. And so this is also actually, it's a pointwise maximum of linear functions, and so that this is a convex function of x. Okay, so that's a little subtle, not immediately obvious. If x was a general matrix, right? So if it was not square or anything like that, then you might want to talk about what is the maximum eigenvalue of x. That's also called the spectral norm of x, right? So you'll sometimes see this notation. This is the spectral norm. Yeah, sorry, it's the maximum singular value of x, which is also called the spectral norm. Again, the fact that I'm saying it's the spectral norm, and I'm kind of giving away the fact that it's a convex function because it's a norm, but it's not immediately obvious as to why, if I take the SVD and I look at the maximum guy on the diagonal, why that's a convex function in x. But again, because I can write this as max over u and v of u transpose x v, such that the norm of u is equal to the norm of V, which is equal to 1, right? So if you're not familiar with this, you should be. This is an alternate definition of the largest eigenvalue. It's again which singular vector on the left and which singular vector on the right should I be looking at to maximize this this value. And again, this is a bunch of maxima of linear functions in X, and so this is f of X is actually convex in X. So this is a convex function of the matrix X. So these are some not so obvious examples, but they all arise from the same intuition. If you ever want to understand why any of these is true, you should just be thinking in your head about the intersection of epigraphs of functions. Okay, that's good. Let's see, I'm going to put that up there. There are some other similar such interesting properties, like it should be fairly obvious to you that a non-negative weighted sum of convex functions is also convex, right? So suppose W1 and W2 are both positive, and I take these two functions which are convex and I add them up, then f of X is convex. Now there are many ways in which to see this. If you want to talk about it in terms of the, one trivial way to see it mentally, if you want, is if you take the second derivative. If it's a one-dimensional function, you take the second derivative. It's positive here, it's positive here. I'm taking a non-negative sum, so the second derivative of this guy is going to be positive. If you're thinking of a higher dimensional function, that same intuition holds except for Hessians. If the Hessian is greater than equal to 0 here, the greater than equal to 0 here, and by that you mean it's positive semi-definite, then the non-negative weighted sum of positive semi-definite matrices is also true. So there are several ways in which you can convince yourself that that a non-negative weighted sum retains convexity. And similarly, while this might be clearly obvious, a slightly more subtle version of it is when you move from finite sums to integrals. So if you're ever looking at something like integral W of y f of x y dy over all y in A. So you have some set A, could be an infinite set. Your weight is positive at every point in your set. So this is a positive weight everywhere. Now f of x y is convex in X for every point y. Okay, so just like f1 of x was convex, f2 of x was convex, I'm saying that fx comma y1 is convex, fx comma y2 is convex, and so on. For every point y in the set, fx comma y is convex in X. Then this function, which is a function of x, since I've integrated out y, this function is also going to be convex. Okay, so I mean, it's just a generalization of this earlier property. So I think that you guys should definitely read through Boyd, like the chapters 2 and 3. He'll give you a bunch of examples of these kinds of properties. Some of the properties may not be as useful. Like I personally have not found perspective of a function to be as useful. I mean, I'm sure it comes up in a lot of places, but things like max is definitely going to be a useful thing to sort of internalize, especially when you're taking infinite maxima. There are some other properties of convex functions that you guys should get used to thinking about. One of them is that convex functions have to be continuous. Okay, and the easiest way to see that is by looking at the epigraph again. So the reason that you cannot have a discontinuity in a convex function is that if the convex function jumped, then if you looked at this set is not a convex set, because if you consider this point, a point here and a point here, then every point in the line between them does not lie in the set. So whenever you have a discontinuity in a function, the epigraph immediately becomes non-convex, and so you can clearly see why this can't be true. Discontinuities are allowed at endpoints. So if you're at the endpoint of an interval, then a discontinuity is disallowed. So basically, if the function's like this, and then outside this interval, I define it to be infinity. Like I think what Barnabas had defined to be the convex extension of any function to all of the reals. then that's allowed in some sense. If you're, I mean, at the boundary, at the boundary of an interval and it jumps at the boundary, that's fine. I mean, that doesn't, the real problem comes when after the discontinuity you still define your function after that, then the epigraph becomes non-convex. But it should be clear that convex functions are continuous. Now, convex functions don't have to be differentiable. So you'll see later on in the first order methods that there's a clear difference in convergence rates for minimization of smooth functions and minimization of non-smooth functions. So you should start getting, you should perhaps stop thinking of all convex functions as looking like this, because most interesting convex optimization problems will be minimizing non-differentiable functions. And I mean, this is true even if the function, I mean, we'll talk about it, but this is true even if the function is strongly convex or strictly convex. So I mean, many times when people draw a non-differentiable function to you, it's going to look like mod x, or it's going to look like something like that with a kink, but it does not need to be linear for you to come up with examples in which it's not differentiable. I mean, it could be strictly convex. So this is not strictly convex, but the function could be strictly convex and still not differentiable. And there are several easy examples to see, like for example, if the function is like e to the x when it's less than 0, and something like 2 e to the x minus 1 when it's greater than 0, something like that. So it's e to the x on one side and it's 2 e to the x minus 1 on the other side. I mean, at 0, here the value is 1 and here the value is 1. So I mean, it's continuous. It's just that the differential is 1 here and it's 2 here or whatever. So it's not differentiable. So it's this function is strictly convex, just not differentiable at 0. And there could be, you can come up with many more, but basically it's not this is true for strong convexity also. So it could be strongly convex as well. And the same thing would hold true. And similarly, like for example, max of e to the x and e to the minus x, something like that, that is also going to be, it's going to be a convex function, but it's not going to be differentiable at 0. Okay, that's good. So just keep that in mind. Okay, now let's move to talking about these concepts which are going to be super important through the course, which are okay, how do I explain this? So there's convexity versus strong convexity, okay, and as a parallel to that there's going to be the function being Lipschitz and the gradient of the function being Lipschitz. Lipschitz gradient, if you okay, so and there are parallels between all of them. So the same way that there are parallels between these two, there's going to be parallels between these two, and these two are going to be connected as well, and these two are going to be connected as well. And we'll just look at that, and it's good to sort of wrap your head around all of them. Okay, so I mean, let's start off with the most simple one. The definition of Lipschitz is something that people should be familiar with even before you come to this course. A function is Lipschitz if you can write down something like this. Okay, so basically the function cannot vary too quickly. Lipschitz is a way to control the smoothness of a function. You say a function is Lipschitz when if x is close enough to y, then f of x must be close enough to f of y. It can't jump too quickly. So it's a controlled growth in some sense. An alternate way to write this is that the gradient of the function, okay, so if the gradient exists, let's say, at all points is at most L. So I mean, we'll talk about subgradients later on, probably next week. I might not have enough time to cover it today, but subgradient you could think of as if it's not differentiable at a point, then you can define a set of hyperplanes. So basically, if you have a function like this, then the gradient is defined at all these points except at 0. And at 0, you define a subgradient to be basically the slope of any hyperplane that lower bounds the function. So basically, another way to write down what Lipschitz means is to say that the gradient of the function is bounded by L everywhere, or the subgradient is also bounded by L everywhere. I mean, that's the corresponding definition, but if you don't know what subgradient is, you'll learn it next week. Or if you understood by the intuition, it's just at any non-differentiable point, it's the slope of any line, any hyperplane that lower bounds it. Okay, so that's Lipschitz. Sorry? The equivalence is not obvious. If I have time, I'll prove it. No, it's not. But I mean, in some sense, it proceeds in the same intuition of what you mean by differentiability by crossing over and stuff like that. I mean, like take down y minus x, x tends to y, things like that. So it follows from that same intuition. Now for convexity, so while this says it cannot grow more than a certain amount, convexity is kind of saying that it grows at least as fast as some amount, right? So it's saying that f of y is at least f of x plus gradient at x transpose y minus x. Okay, so in some sense this gives, this is like the opposite kind of definition. Okay, it's more like, if you wanted to look at it this way, this is saying something like f of y minus f of x grows at least as fast as the gradient times y minus x. So it's more like, it's just this is saying at most and that's saying at least, so it's sort of the other way around. And so this kind of controls that the function must grow at least as fast as something. This says the function has to grow at most as fast as something. Okay. Now, I mean, this is the first order definition of convexity. The corresponding second order definition would be that, the Hessian, which is del squared f, is positive semi-definite. Okay, so the Hessian is PSD. Now, what about strong convexity? Strong convexity is going to say pretty much the same thing, but quantify how much the difference is. Okay, so it's going to say, the same thing that I require f of y to be at least f of x plus gradient transpose y minus x, but I'm also going to tell you by how much, and that's a second order term here. Okay. So I mean, if you want to imagine it, then what the first order definition is saying is that if I take a point y, and this point is here, so if this is y and this is x, then it's saying that convexity just says that f of y has to be more than starting at f of x and moving in the direction of the gradient an amount of y minus x. And what strong convexity says is that, sure, you start at f of x, you move an amount in the gradient direction of y minus x, but it will also tell you that this difference between the hyperplane and the function is at least y minus x the whole squared. So it's going to just quantify how far away it has to be. So if the difference is growing fast enough, then there's enough curvature in the function. So this is sort of a measure of how curved the function is, and the larger lambda is, the more curved it is. An alternate way to think about it is, people often think about it in this way, is that even when you remove a quadratic from the function, so basically f of x minus lambda by 2 x squared, this is still convex. Okay, so if you want to see that, you can just play around with algebra to see that these two statements are actually the same. So one of them is taking 2 points and talking about it. This is just saying that if I took the function f of x and I removed a quadratic from it, that function is still going to be convex. Okay, so that's fine. I mean, this is not obvious at all, right? I mean, if you add a convex function to a convex function, it's going to remain convex. But I'm subtracting a quadratic from a function, and I'm retaining convexity. So it's just another way of looking at it. The corresponding second order way of looking at this is to say that the Hessian is at least lambda times the identity. So that is, in other words, the smallest eigenvalue of the Hessian here is just, you just know that it's going to be 0 or positive. And over here, you're saying that the smallest eigenvalue of the Hessian is at least lambda. Okay, so if you should know this notation by now. This is again for positive semi-definite matrices. We say that A is greater than or equal to B. So if you don't know it yet, then A is said to be greater than or equal to B when x transpose AX is greater than or equal to x transpose BX for all x. Or another way to say it is that A minus B is PSD. Okay, so, but I mean, I just think about it this way usually, that when you're saying that one matrix is greater than the other, you just mean that all quadratic forms of this form, it's larger. So, and that basically means that, I mean, the eigenvalues of this matrix are all lambda. So lambda times identity is just lambda, 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 lambda. So the eigenvalues of that are all lambda. And if this has to be greater than that, then basically all its eigenvalues must be at least lambda. So that's what the interpretation of that is. Now, I mean, another useful way to think about convexity is through the 0th order definition, which is the Jensen's inequality, right? So Jensen's inequality basically says that f of the average is smaller than the average of the f's, right? So so that's f of tx plus 1 minus ty. So if I evaluate f at the average point between 2 points, then it's lower than the average. So it's less than or equal to t f of x plus 1 minus t f of y. Okay, so this is another natural way to think about convexity. Now what strong convexity says is again that sure, the f of the average is going to be less than the average of the f's, but how much lesser is it? It's going to be able to quantify and tell you something like this is going to be less than lambda times t times 1 minus t times x minus y the whole squared. Okay, so this is the statement for strong convexity. So just like so this basically looks like the Taylor expansion of the function. So just like strong convexity quantifies how much the gap is for the Taylor expansion, it also quantifies how much the gap is for Jensen's inequality. And it says that this side is less than this side, but by at least that much. Okay. So this is another useful way to think about strong convexity. And you should think about strongly convex functions as being curved. Now again, strongly convex functions don't have to be differentiable. So even though I mean, you're imagining strongly convex functions as being curved, they could just be something like this. Okay, so they could just they could be non-differentiable at some points. And then I think what should be so I mean these strong convexity and Lipschitzness and even gradient being Lipschitz are often functions of the domain. So when you change the domain, you could change the nature of strong convexity or the Lipschitz constant. So I mean, just as an example, if you're talking about the function x squared, okay, so if you're talking about the function x squared, then x squared if I took it over its entire domain, x squared is not, it's not Lipschitz continuous, right? Because its gradient is 2x, and if I ask for is the norm of the gradient less than equal to any constant, and the answer is no. So x squared is not Lipschitz continuous over the entire domain. But as soon as I restrict the domain, as soon as I restrict it to anything like -5 to 10, whatever, if I'm considering x squared in some bounded region, it immediately becomes Lipschitz continuous with a bound of 20. So its Lipschitz constant is 20. And if I took the domain to be different, it is Lipschitz continuous with a different constant. So this might sort of convince you that Lipschitzness is sort of cheating in some way, but that's a very contrived, it's a contrived example. There are functions that are Lipschitz throughout the domain, but what you should know is that every function is Lipschitz on a bounded domain. So as soon as I bound the domain, every function becomes Lipschitz. You just calculate its maximum gradient or subgradient value throughout its bounded domain, and that's its Lipschitz constant. Okay, but it's still, I mean, there are many functions which are not like this. But you should realize that whenever someone says L, they actually implicitly mean L of the set that it's being defined on. Okay, that's like the implicit definition. And similarly, when you talk about strong convexity, now if I take a function like e to the x, right? So if I take a function like e to the x, its second differential, okay, I'm just going to differentiate it twice, and that's just e to the x. And if I ask you, is its second differential lower bounded by a constant? The answer is no if the interval is the entire real line. If I'm considering from -infinity to infinity, then at -infinity, at -infinity, this value is 0. So its second differential is not lower bounded away from 0 on the real line. But as soon as I bound it between, I don't know, -5 and 10 again, then this immediately becomes strongly convex on that domain with an appropriate lambda of e to the 5 or whatever. Or e to the -5 rather, something like that. So again, strong convexity could be a function of your domain. And that's again important to recognize. We'll often say something like lambda, and there's an implicit lambda of the set that you're considering. So again, many functions are strongly convex everywhere. So for example, x squared is actually strongly convex no matter what domain you consider, because x squared, its second differential is 2. So no matter what domain you're considering, it is bounded away from 0. So it is strongly convex throughout its domain. So there are functions like this, and we'll often come across functions which are strongly convex throughout their domain also, but just to remember that this lambda often means lambda of S, of the set that you're considering. So the last thing that we need to talk about right now immediately is the gradient being Lipschitz. And the gradient being Lipschitz is correspondingly it's the opposite condition of strong convexity. Okay, so the gradient being Lipschitz is going to look like strong convexity, but it's going to be one level stronger than just Lipschitzness. So it's going to say something like the gradient of f at x minus the gradient of f at y is lower bound, is at most some other constant, whatever, times x minus y. Okay. Now, again, this is not immediately obvious, but this is equivalent to saying that the Hessian of f is at most L prime. Okay, so the strong convexity again said that the lowest eigenvalue of the Hessian is at least lambda. This is saying that the largest eigenvalue of the Hessian is at most L prime. Okay, and so in some sense it's bound. It cannot grow too fast. So strong convexity says it has to grow at least as fast as some amount. It has to grow at least as fast as this plus some linear term plus some more. It has to grow at least as fast as that. What this says, it says that it cannot grow faster than a certain amount, and you can actually write exactly that form. You can write f of y is at most f of x plus gradient at x transpose y minus x plus L prime by 2 times y minus x the whole squared. Okay, so you'll see that this is pretty much exactly the form of strong convexity, except the sign is the opposite way around, and it's of course a different constant, a larger constant. Okay, so again this bounds, it bounds the rate of growth. It's a measure of how you want to control how fast your function can grow. And if your function cannot grow too fast, then perhaps its Lipschitz could be, its gradient could be Lipschitz continuous. So this is the same way as Lipschitz is slightly weaker. Not slightly, it is much weaker than the gradient being Lipschitz. Same way convexity is much weaker than strong convexity. So you'll see in the course that the rates of, and you could consider all combinations of these. Like you could consider functions that are convex and Lipschitz, strongly convex and Lipschitz, strongly convex and Lipschitz gradient, and so on. And you'll see that as you add one of these properties, the minimization just becomes easier. So basically, it's easier to minimize a function with Lipschitz gradient than it is to minimize just a Lipschitz function. In particular, a Lipschitz gradient function has to be differentiable. It has to be, only differentiable functions can have a Lipschitz gradient. And so if your function is smooth, that is, it's differentiable and it has a Lipschitz gradient, it's going to be much easier to minimize than if your function is non-smooth. So you can have, any function just looks like that. Any function like that is Lipschitz. In particular, if it has to be convex also, then it cannot grow too fast. But these can be non-differentiable. You'll see that functions that are just Lipschitz are harder to minimize. In exactly the same way, functions that are strongly convex are going to be easier to minimize. You have some additional property of the function that you can play with. And functions that are just convex are going to be harder to minimize. So it's a good idea to kind of wrap your head around these definitions. They are, I'm sure that you could write some sort of a first order condition for this, but I think the most useful characterization of these functions is the first order one, right? So the first order for strong convexity and the first order for gradient being Lipschitz should really try and internalize these, the fact that they're trying to say slightly opposite things about the function. Does anybody have any questions? It's quite easy to prove something like this. Okay, so if you're starting off with, this is the definition of the gradient of a function being Lipschitz. So this is by definition. It's actually quite easy to get something like this because of Taylor's theorem. So you should just get used to thinking of Taylor's theorem. There's a particular form of, there are several forms of Taylor's theorem when you talk about the remainder term, but there's a particular form of Taylor's theorem which goes like that f of y actually equals f of x plus the gradient at x times y minus x plus something like y minus x transpose the Hessian at some point z times y minus x. So where z is some point between, on the line segment between x and y. Right? So this is one form of Taylor's theorem. I think it's called the Legendre form or Lagrangian form or something like that. There's some, there are different ways in which people state what the remainder term is. But basically this is the first order Taylor expansion with the second order error term. And this z has to be a point on the line segment between x and y. And as soon as you've written down something like this, this holds with equality, you immediately have that the Hessian is, oops, there was an identity here. That the Hessian is basically at most a constant times the identity. So as soon as you put that in, there's a half, right? So you just put in this del square f is at most L prime times the identity, and the L prime is just a constant that comes out, and y minus x transpose times the identity times y minus x is just y minus x the whole squared. So basically this property of Lipschitz functions follows immediately from Taylor's theorem, and so does this. Like if you started off with a different statement about um, about strongly convex functions, you could actually derive this one. So all of these are actually interchangeable. If you know one, you can prove the other, and so on. You can show that all those definitions are equivalent. That is, you can go from the 0th order definition, which does not use gradients, to the 1st order definition, which uses gradients, to the 2nd order definition, which uses the Hessian, and similarly over here. These are actually all equivalent and interchangeable, as long as the function is, I mean, of course, this is only true if the function is differentiable. If the function is not differentiable, then you just have to stick to the 0th order definition. Also, if the function is not differentiable, then this statement holds true for the subgradient of the function. So if you don't have the gradient of the function, you can still use the subgradient of the function, and it will still be true. It will hold true for all subgradients of the function. But again, maybe you want to see that after you learn what subgradients are. But again, I mean, broadly, they're just a generalization of the gradient. If it's not, I mean, the gradient is a slope. If there's not one slope but many possible slopes, then all of those are subgradients. Okay, any questions? Yep.
Is that a matrix form? The one under which you're saying the gradient of that?
No, the gradient is a vector.
Yeah, and it's still a normal term.
So it's a vector norm, right? It's the 2 norm. Okay. Any other questions? Okay. So there's one more subtlety here which that question actually raises, and I might as well come to now, is what norm is all this in? So all this presently when I wrote that norm, I meant the 2 norm, but actually if you are familiar with normed spaces, then you can assign any norm you want to the Euclidean space, for example. So if you're working in Euclidean space, you're working in Rn, there's no reason for you to stick to the 2 norm. You might want to associate the 1 norm with your space. So a function, when you define strong convexity, you actually have to specify which normed space you're working in. Okay? So as an example of why you would want to do something like that, in many cases, you will come across optimization problems in which you're trying to work with probability distributions. So you're trying to maximize or minimize, or maximize some entropy or minimize something else, some Kullback-Leibler divergence between couple of distributions. And so you're working in the space of distributions, which is the probability simplex. So it's basically, it's normally donated by delta n, and it's the set of all points where if you sum them up, you get 1, and each of those points is positive. So you're working in the probability simplex. Now, when you're working the probability simplex, there's another norm that becomes natural to use, which is the 1 norm. The 1 norm of so often it will be less than equal to 1 if you're talking about the entire set. And the 1 norm is very natural to use in these when the 1 norm is bounded by 1 for everything in the probability simplex. And you'll actually see that which norm you choose will affect both your convergence rates and the properties of your algorithm. Now, why will it? The reason is that when you analyze convergence rates, it will depend on the Lipschitz constant of the function. It will depend on the diameter of the set. Now, diameter of the set can be measured in different norms. So if I'm working in a particular set, this set has the 1 norm bounded by 1, but the 2 norm having a different bound. Similarly, if I'm asking for the Lipschitz constant of any function over this set, the Lipschitz constant could actually be, I could measure it in 2 norm, or I could measure it in 1 norm, or infinity norm, or some other norm, right? So basically, the maximum norm of the gradient on your set depends on which norm you choose. And you'll see that different choices of norms lead to different diameter bounds on your set and different Lipschitz constants. And you'll actually see that functions like the entropy function, okay, so sum of xi log xi, this function is not strongly convex with respect to the 2 norm on this set, but it is strongly convex with respect to the 1 norm on this set. Okay, so I mean, many times if you're dealing with something like this, or you want to deal with something like this, then you would rather choose the one norm and deal with it because it's then a strongly convex function on your set. So the corresponding definition of a strongly convex function with the one norm would just be that you require your function to be f of y to be at least f of x plus gradient transpose y minus x plus lambda by 2 times y minus x one norm squared. Okay, so so you should, the correct way to state things is to actually say that a function is not just strongly convex, but you say a function is strongly convex with respect to this norm. Okay, and choosing different norms. So x squared is strongly convex with respect to the 2 norm, and sum of x log x is strongly convex with respect to the 1 norm, and so on. And similarly, such a thing applies actually to matrices also, that often we'll be trying to work with special sets. Like if you were working with the Euclidean ball, you'd probably choose the 2 norm, but if you're working with the probability simplex, you'd probably choose the 1 norm. The same thing holds for matrices also. If you're working with one set, you'd choose the spectral norm, which is the largest eigenvalue. You should work with a different set, you'd rather choose the nuclear norm, which is the sum of all the eigenvalues, and so on. So that was actually a good question when you ask which norm is this, and it really matters for your definition of Lipschitz gradient and strong convexity. So the right statement over here is actually that if I choose some particular norm for defining Lipschitzness, then the equivalent thing over here is that the dual norm of f is of the gradient of f is bounded by L. If you don't know what the definition of a dual norm is, you'll find out later in the course. But the 2 norm is the dual of the 2 norms, so putting 2's everywhere doesn't hurt at all. But the 1 norm and the infinity norm are dual norms, and so the right definition when you use the when you use one of the norms here is to use the dual norm over here. And again, that's easy to prove. Perhaps I'll prove that later in the course, or maybe today if there's time. And similarly over here, when you define something to be, when you define it to be a Lipschitz gradient, for now we'll assume that everything's just the 2 norm. But just remember that you can actually define it in a different way. You can actually define it in terms of actually a dual norm and the actual norm over here, which is what you might want to do later in the course. Or just keep in mind that it doesn't always, you don't have to always be working with the Euclidean norm. There are other norms that you could work with. And the properties of the function will depend on the set that you're working over, and so just as I said that L and lambda are functions of the set, they are also functions of the norm that you choose to work with. Okay, any questions? Yep.
The probability simplex, the L1 norm is upper bounded by 1, so why is it not 1? The distribution is sum to 1.
No, yeah, I mean, I was just saying that, I mean, sometimes it could be that you're working with the interior of the probability simplex. You're working with all sum of xi is less than equal to 1. You could work with the probability simplex also, in which case it's equal to 1. That's fine. I mean, sometimes you work with both. I mean, in one case, if you want to imagine it in 3D, then in one case you're working with the surface of a triangle, just that particular hyperplane, and in one case you're working with the entire volume of what's between the triangle and the origin. So it's just like depends on which set you're performing your optimization over, and that's all. Yep.
Will different choices of norms lead to different gradients? Is it right?
Will different choices of norms lead to different gradients? No. The gradient of the function will remain the same. How large the gradient can get will depend on which norm you choose to evaluate how large, right? So the norm really comes in evaluating how large can the gradient get. So the norm of the gradient, but the gradient itself will remain the same. It will look like 2, 3, 1, 5. It will look like a vector. And do you want to calculate the 2 norm of this vector or the 1 norm or the infinity norm?
The direction is the same, but the value will change.
So there's no value of the gradient in higher dimensions, right? So the gradient is a vector. It doesn't have a value. It has a norm depending on what norm you define. Yeah.
So is convexity
No, right? So convexity is stated independent of norms. But if you want to go one more step, then it depends on the definition of inner product. So basically, you could have actually different inner products defined, and you could define convex. But it's, I mean, for this course, I think it will always be the standard inner product. It will always be the AI, BI. It will be that inner product. Or for matrices, the corresponding matrix inner product. It's always that inner product, but you'll change the norms. So for the purposes of this course, you should think of the dot product as being the same, but the norms as possibly changing. Now, when Ryan will use it in class in the first coming few lectures, it'll always be the 2 norm. So when you see nothing stated there, you just assume that it's the 2 norm. But then when we get to doing, like we'll be doing things like nuclear norm minimization for matrix completion or things like that. You'll be doing maximum entropy, something like that. If you're working with things like that, then you'll actually end up defining different norms. And they actually lead to different algorithms. So if you do gradient descent, but with respect to the one norm and the entropy, it leads to a different algorithm, which looks different from the normal gradient descent. So you'll see that actually gets a better rate of convergence than if you just assumed it was the 2 norm. So basically, if you want to take advantage of the space that you're working in to get a better rate of convergence. So, and you'll see how to do that. So basically, like what Ryan did last class was he showed that the rate of convergence of gradient descent was 1 by k. What you'll see later on is that if you there's a Lipschitz constant there. It's actually L times something by k. And what you'll see later on for projected gradient descent, that is, you do gradient descent, but you keep projecting onto a set, is that I mean, how many steps you'll need, I mean, how close you get after k iterations will be the Lipschitz constant times the diameter of the set by k. So that's what it'll look like. And so your choice of what the gradient, how you measure the gradient and how you measure the diameter will affect your rate of convergence. Any questions? Let's see. Now, a useful thing about strong convexity, which is very useful, is that if f is strongly convex and I add, so this is strongly convex and I add a convex function to it, then f plus g is still strongly convex. Okay, so I'm adding a convex function and a strongly convex function, the net result is still strongly convex. And maybe that's easiest to see from the 0th order definition. So if, okay, maybe I should define this as this f is equal to h plus g. So h is strongly convex and g is convex. So if in this definition, if I substitute f as h plus g, and I use the fact that the h term will give me this, the g term will just give me this, and then I combine that, you'll be able to see that, I mean, you write down the 2 definitions. So one is that h of tx plus 1 minus ty is less than equal to this entire thing with this term, and then you write down that g of tx plus 1 minus ty is less than equal to just this term without this term, and you add them up, then you get g plus h, which is f, and here you get g plus h, which is f, g plus h, which is f, and you still have this term. So basically, f will still look like tf of x plus 1 minus tf of y and this extra term. So that extra term that comes because h is strongly convex carries forward to f. So it's pretty clear from the 0th order definition that when you add a strongly convex function and a convex function, the resulting thing is strongly convex. So this is particularly useful in ridge regression. So when you're doing ridge regression, you're doing something like minimizing, or let's say if you're just doing least squares regression, you're trying to minimize something like ax minus b the whole squared. Okay. Now this looks like x squared, so you might think that this is strongly convex, but like the a is actually quite important. So if you take the second derivative of this, then you actually get a transpose a. Okay, so the Hessian is a transpose a. Now a transpose a is if it's not full rank. So if A is not full rank, so suppose A is M cross N and X is in Rn. Okay, so I'm doing some regression where I have M constraints in N variables. The Hessian is going to be an N cross N matrix. Okay, so it's N cross N. If M, the number of constraints, is less than your number of variables, that is, this is an under constrained system, A is going to be of rank M. Okay, so M is less than N. So of course, so if M is less than N, of course the rank of A cannot be N. It has to be the smaller guy. It has to be M. So the rank of A transpose A is M. Okay, so the rank is N cross N with rank M. Okay, so clearly it has a bunch of 0 eigenvalues. So it has N minus M 0 eigenvalues. So it's not strongly convex in general, right? So in general, this function is not strongly convex. If M was greater than or equal to N, then this could be strongly convex. It depends on whether A was full rank or not. So basically, this function is not strongly convex in general, but as soon as I add a ridge penalty, this is always strongly convex no matter what A is. Okay, so remember x squared, when you differentiated it, you got 2. Well, the same thing holds over here. This is x transpose x. When you differentiate it twice, you just get 2 times the identity. And so this is strongly convex and it has strong convexity parameter 2. Lambda by 2 times this is also strongly convex with parameter lambda. Okay. And this is strongly convex almost by definition. Remember that, once I subtract a quadratic, it still remains convex. Well, when I subtract a quadratic, it's 0, which is convex by definition. So this is always strongly convex. And that's really useful because now the sum is also always strongly convex, which is pretty cool. The Hessian is now going to be A transpose A plus lambda times the identity. So this is, first of all, it's going to be full rank. It's going to be N cross N. It's going to have lowest eigenvalue lambda. And now this allows you to do many things. I mean, first of all, if you could, you would just differentiate it, set it equal to 0. You can invert this matrix, but you could not have inverted the earlier matrix. But suppose this was not something that you could just differentiate it form closed form for. Suppose it's not ax minus b the whole square, but some logistic loss or some other loss function over here. It could be a non-strongly convex loss function. Could be the hinge loss or whatever you want. You add a ridge penalty to it, it immediately becomes strongly convex. You can apply first order methods to minimize it. And because strongly convex functions are easier to minimize than convex functions, which you'll see in the coming lecture, then you'll actually get a better rate of convergence because of this. So many times people add a ridge penalty for statistical purposes. That is, you actually get better estimation and guarantees. But from a computational point of view also, it makes a lot of sense because it immediately guarantees strong convexity and immediately guarantees faster methods to minimize using first order methods if you need to. Because as I said, the L2 one, this can be minimized in closed form, but in many cases, if this is like a hinge loss or something else, you can't minimize it in closed form. But as soon as you add a strongly convex penalty to it, you can use first order methods. Okay, any questions? This is a very cool property that's very useful to keep in mind. And it's very easy to think that ax minus b the whole squared is strongly convex because it looks like x squared, but it's not. So just keep that in mind.
Is that true that only because all over like the Bayesian sum is if we add a
Well, yeah. So yes. So well, the 2 norm squared is strongly convex with respect to the 2 norm. If you added 3 norm squared, I'm not sure if it's strongly convex. I don't know. I'm not sure if it's strongly convex anymore. You'll have to just sit and verify one of these properties. I don't remember if the 3 norm squared is strongly convex or not. But usually the other option is something like the 1 norm, which is not strongly convex. It's not strongly convex with respect to the 2 norm. Maybe another useful definition over here for convexity is that the gradient of y minus the gradient of x transpose y minus x is always greater than or equal to 0. So you might want to convince yourself that something like this holds true. It's a very useful property. I mean, of course, in one dimension, it just means that if I increase from x to y, then the gradient must increase. So, if I'm going in a positive step, then the gradient's always increasing. But such a statement about convex functions that the gradient is increasing. So if I take a positive step, then the gradient has also increased. Such a thing holds true in higher dimensions as well, except there's a transpose there. You might want to convince yourself that that's true, and that's actually easy to see by looking at the definition of convexity, the first order definition. So if you look at this first order definition of convexity, and you write the same thing down, but with x and y flipped. So if you wrote f of x is greater than or equal to f of y plus gradient at y transpose x minus y. So you wrote down both those equations and you added those two equations, then these terms would cancel, and what you'd be left with is something like this. So you want to convince yourself just that such a thing holds true in higher dimensions, because that's another way of stating convexity, saying that the gradient is always increasing, which is true in 1D, but in higher dimensions, this is the corresponding statement. And now for strong convexity, instead of being greater than or equal to 0, you actually have greater than or equal to lambda times y minus x the whole squared. So it sort of gives you an amount by which the gradient is increasing. So this is another useful characterization of strongly convex functions. You might find it useful either on a homework or in life, in a proof or something like that. Let's see if I missed anything else. Any questions? I think that's all I had for today. If you have any questions, then you can ask me, but otherwise I'll send out a mini write-up later on today. Thank you.